In Chapter 10, we're learning about sequences and series, and you see that in your notes I've added this scale of learning, and it kind of describes or gives you an idea of where you are as we're going along. Do you know? Can you do? Level 3 is pretty much meeting standard. Level 4 is you're exceeding expectations. So we start this chapter with sequences, series, and sigma notation. And this is vocabulary that you've been exposed to before. List of numbers in a specific order is a sequence, and a sequence can be infinite or finite. It is finite if it has a certain number of terms. It is infinite if that sequence goes on forever. The sequence is unique if it has an explicit formula. So in example 1, we're just using the pattern that we observe to find the next 4 terms of the sequence. Now, it is possible to have more than one possible correct answer, but ideally what we're looking for is, based on what's happening in the previous terms, let's continue that pattern. So in part A, I look at my first 2 numbers, 32 to 16, and that's about half. Or it is half, excuse me. And then, oh look, that's half again. And oh look, that's half again. So let's take half some more. The instructions are asking us to find the next 4 terms. So for part A, I'm going to say that the next 4 terms are half of 4, which is 2, half of 2, which is 1, half of 1, which is 1/2, half of 1/2, which is 1/4. In part B, from 1 to 2, okay, I'm doubling it. From 2 to 4, hey, I'm doubling it again. And then from 4 to 7, uh-oh, that didn't work. So let's start from the beginning again. So instead of looking at it as multiplication, let me look at it as addition. From here to here, I'm adding 1. From here to here, I'm adding 2. Here to here, I'm adding 3, 4, 5, 6. So let's add 7, 8, 9, and 10. Pause your video to work through the Your Turn, which is part 1C. Another kind of formula that we can use is a recursive formula in which we describe the current term based on its previous term. So, for example, here, this term is being described as -2 times the term before it. And in the instructions, they're asking us for the 6th term of the sequence. So in order to use this formula, I have to find a sub 2, a sub 3, a sub 4, a sub 5, and then I can find a sub 6. So a sub 2 is going to be -6. A sub 3 is going to be +12. A sub 4 will be -24. A sub 5 will be +48, which means A sub 6 is -96. For part B, once again, it's being described in terms of the previous term, so I take each previous term, multiply it by 2, and then take that value minus 7. So I start with this 8, I multiply it by 2, and I subtract 7 from it. So 2 times 8 is 16. 16 minus 7 is 9. So A sub 2 is 9. A sub 3, I'm taking this 9, multiplying it by 2, I get 18. Minus 7 is 11. A sub 4, I take the 11, multiply it by 2, I get 22. Minus 7 is 15. A sub 5, 2 times 15 is 30. 30 minus 7 is 23. And finally, A sub 6 is 2 times 23, which is 46, minus 7, giving me 39 as my 6th term. I mentioned previously that sequences can be infinite or sequences can be finite. When we're talking about infinite sequences, we can think of them as behaving like some functions behave. So previously we talked about how a function can approach either positive or negative infinity, or we've had functions that kind of flatten out towards a specific value. Sequences can do the same. When a sequence approaches a specific value, we say that it is convergent. Whereas if a sequence kind of goes to positive infinity or goes to negative infinity, we say that it is divergent. So in these examples, we're trying to find out whether the sequence is convergent or divergent. So let's find a few terms. A sub 1 is 64 over 2, which is 32. A sub 10 is 64 over 20, which is, I believe, 3.2. A sub 100 will equal 64 divided by 200, giving me 0.32. 0 sub 1000 will be 64 over 2000, giving me 0.032. And what I'm hoping you would notice is that as this number is getting bigger and bigger, the result is getting closer and closer to 0. It'll never hit 0, it'll never equal 0, but it will approach that. So we will say that this one is convergent. In this next example, notice that the formula is written recursively, and that every time I'm adding 4 to the previous term. Well, if I take 9 and I add 4 to it, I get 13. I add another 4, I get 17. And what I'd hope you'd notice is that this is going to keep getting bigger and bigger and bigger. It's going to approach infinity. Therefore, this is divergent. A sub 1 equals 3 times negative 1, which is negative 3. A sub 5 will equal negative 3 as well. How about a to the 10th? Well, that's going to equal 3. How about a to the 100th? Well, that's also going to equal 3. And it should be apparent that when n is even, it's going to be positive 3, and when n is odd, it's going to be negative 3. So it's just going to keep bouncing between negative 3 and positive 3. It's not flattening out towards a certain value. This is divergent. Next bit of vocabulary that you're familiar with is that a series is a sum of the terms in a sequence, and similarly, it can be finite or infinite. But when we're finding the nth partial sum, we are adding a finite number of terms, and we notate it by capital S sub n. So in example 5, part A, I'm trying to find the 6th partial sum of this sequence that is recursively defined. So in order to do this, I have to figure out what a sub 1 is, what a sub 2 is, what 3, 4, 5, so on and so forth. All right, so here we go. For part A, I know what a sub 1 is. A sub 2 is going to equal 0.5 times the last value, so that's half of 8, which is 4. A sub 3 is half of 4, which is 2. A sub 4 is half of 2, which is 1. A sub 5 is half of 1, which is 1/2. And a sub 6 is 1/4. And so we're going to take our calculator and add all that together. So 4 plus 2 plus 1 plus half plus 1/4. And we get 7 3/4. or let's write that as an improper fraction. (31/4). In part B, we're finding this seventh partial sum of this explicitly defined sequence. So a sub 1 is going to be 3/10. A sub 2 will be 3/100, and maybe it would be good to write this as a decimal. This is 0.3. This is 0.03. A sub 3 is going to be 0.003. A sub 4, 0.0003. A sub 5, 0.00003. A sub 6, 1, 2, 3, 4, 5. And then finally, a sub 7 is 0.0000003. So the partial sum of that, s sub 7, will equal 0.33333. How many of these? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I mentioned earlier that a sum can be partial or infinite. And looking at this, I'd hope that you'd kind of get the idea that if this had been an infinite sum for this sequence, my infinite sum would have been 1/3. The last bit of vocabulary in this lesson has to do with sigma notation, which is just another way of notating a series. It's a summation. In this notation, this 1, this n equals 1, is indicating that the first term of the sequence that I'm including in my sum is, in fact, the first term of the sequence. This k tells me that a sub k is the last term of the sequence that I am including in my summation. So in example 6, this notation is telling me that I want to sum the first 5 terms of the sequence given by this explicit formula. Okay, so a sub 1 is 1 squared minus 1, which is 0/2, so that's 0. A sub 2. A sub 2 means I'm taking 2 and plugging it in for n, so that'll be 4 minus 1/2, which is just 3/2. A sub 3 is 3 squared, which is 9, minus 1/2. 9 minus 1 is 8. 8/2 is 4. A sub 4 is 4 squared, which is 16, minus 1/2, so that's 15/2. And a sub 5 is 25 minus 1/2, so that's 24/2, which is 12. And now I'm going to add all of these terms together in order to find my sum. So that's 3/2 plus 4 plus 15/2 plus 12, and that's 25. Part B, same exact process. The big difference here is that notice we're starting at term 7. So I need to find what a sub 7 is. Okay, so 7 to the 3rd power is 343 minus 7 squared, which is 49. So a sub 7 is 294. A sub 8, 8 to the 3rd power minus 64. That's 448. A sub 9, that's 9 to the 3rd power minus 81. A sub 10, will be 900, because that's 1,000 minus 100. A sub 11, 11 to the third power minus 121, is 1210. A sub 12, 12 to the third power minus 144, 1584, and then finally A sub 13, that's 13 to the third power minus 169, 2028. And now I add all these terms together. And get 7,112. In this last example, notice that it's an infinite sum. Well, we're not going to sit here for infinity and add things on, but we will probably notice a pattern developing and use that in order to answer the question. Okay, so A sub 1 is 6/10. A sub 2 is 6/100. A sub 3 is 6/1000. And so I'm hoping you notice that if I were to add these together and continue the pattern on infinitely, then this would be 0.6 repeating, which is equivalent to 2/3.